Hi everyone, we are José Gamboa and Alexandro Vera, and we are going to talk about Razor, a dynamic voltage scaling technique.
Presentation Index. We're going to split presentation in 6 topics.
Razor. It's a new approach to dynamic voltage scaling technology. It's based on dynamic detection and correction of circuit timing errors. The key idea of Razor is to tune the supply voltage by monitoring the error rate during operation, because this error detection provides in place monitoring of the actual circuit delay. It accounts for both global and local delay variations and doesn't suffer from voltage scaling disparities. It uses a delay error tolerant flip-flop on critical paths to scale the supply voltage to the point of first failure for a given frequency. This eliminates the need for voltage margins that traditional worst-case design methodologies require, and allows digital systems to run correctly and robustly at the edge of minimum power consumption, resulting in significant energy savings. Dynamic voltage scaling. DVS has emerged as a powerful technique to reduce circuit energy demands. In a DVS system, the application or operating system identifies periods of low processor utilization that can tolerate reduced frequency. With reduced frequency, similar reductions are possible in the supply voltage. Since dynamic power scales quadratically with supply voltage, DVS technology can significantly reduce energy consumption with little impact on perceived system performance. Voltage margins. Now we are going to explain the margins factors that can affect the voltage required to operate a processor for a given frequency setting. Critical voltage. The voltage must be sufficiently high to fully evaluate the longest circuit computation path in a single clock cycle. To the critical voltage, they add the following voltage margin to ensure that all circuits operate correctly even in the worst case operating environment. Process margins ensure that the performance uncertainties do not prevent slower devices from completing evaluation within a clock cycle. MV margins accommodate slower circuit operations at high temperatures. The margin ensures correct operation at the worst case temperature, which is typically 85 to 95 Celsius degrees. Noise margins safeguard against a variety of noise sources that introduce uncertainty in supply and signal voltage levels. The sum of these voltages defines the minimum supply voltage that ensures correct circuit operation in even the most adverse conditions. Error rates versus supply voltage. This is an example of an 18 per 18-bit multiplier block, and we are going to explain the result graphic of error rate versus supply voltage. Traditional fault avoidance design methodology sets the circuit voltage at the full margin point. As the figure shows, the multiplier circuit fails quite gracefully, taking nearly 180 millivolts to go from the point of the first error, 1.54 volts, to an error rate of 1.3%, that is 1.36 volts. At 1.52 volts, the error rate is approximately 1 error every 20 seconds, or 1 error per 1.8 billion multiply operations. The gradual rise in error rate is due to the dependence between circuit inputs and evaluation latency. Initially, only circuit inputs that require a complete critical path evaluation results in a timing error. As the voltage continues to drop, the number of internal multiplier circuit paths that cannot complete within the clock cycle increases, along with the error rate. Eventually, voltage drops to the point where none of the circuit paths can complete in the clock period, and the error rate reaches 100%. Clearly, the worst case conditions are highly improbable. The circuit under test experiences no errors and the voltage has dropped 150 millivolts below the full margin voltage from 1.69 volts to 1.54 volts. If a processor pipeline can tolerate a small rate of multiplier errors, it can operate with a much lower supply voltage. For instance, at 330 millivolts below the full margin voltage from 1.69 to 1.36 volts, the multiplier will complete 98.7% of all operations without errors. for a total energy savings, excluding error recovery of 35%. The no-margin voltage is the lowest voltage that can still guarantee error-free circuit operation at 27 Celsius degrees, and the full margin voltage is the voltage at which the circuit runs without errors at 85 Celsius degrees in the presence of worst-case process variations and signal noise.
Razor processor architecture. The main idea in Razor architecture is to tune the supply voltage by monitoring the error rate produced during operation. Because this architecture analyzes current circuit delay, it accounts for local and global variations and doesn't suffer from voltage scaling disparities. Processor pipeline must incorporate a timing error detection part, a recovery mechanism, and the voltage control system. The architecture consists primarily on a main flip-flop controlled by a local clock and a shadow latch controlled by a delayed clock. When both circuits capture the correct data, the sort gates remain low. When an error is produced, the main flip-flop latches the error, but as the shadow works with a delayed clock, it will latch the correct value. Then, the error signal goes to high and activates the multiplexer on the input, allowing that the shadow latch value passes the flip-flop. There are some implementation issues, like the Razor needs that the delay and power overhead from detection circuitries remain minimal, otherwise it would cancel the power savings effect. Methods to reduce power and delay overhead are applied. One of them using the same clock from the shadow latch, but inverting the phase. It results in a delayed clock by half cycle. Not all the flip-flops need Razor. Some of them can reach the required cycle time under the worst-case conditions. This reduces the peak power overhead to 1%. In the architecture, the pipeline recovery mechanism is very important because it guarantees that any process failures will not propagate to register and memory state with an incorrect value. There are developed two approaches to recovering pipeline state: clock gating and counterflow pipelining. In clock gating, Razor detects any error in a pipeline stage. The control logic stops the entire pipeline for one cycle by gating the next global clock edge. This additional clock cycle allows all the stages to recompute its result using the Razor shadow latch as an input. In a general view, recovery logic replaces any previously forwarded errant value with the current value from the shadow latch. Because all stages reevaluate their result with the Razor shadow latch input, a Razor flip-flop can tolerate any number of errors in a single cycle and still guarantee forward progress. If all stages fail each cycle, the pipeline will continue to run but at half of the normal speed. In the graphic A, it shows the pipeline organizations in computation stage, and in the part B, there is shown the pipeline timing for an error occurring in the executing stage. Counterflow pipelining technique. In aggressively clocked designs, it is not possible to implement the clock gating technique. This approach implements the recovery mechanism, introducing negligible timing constraints to the baseline pipeline. Basically, when a flip-flop produces an error signal, pipeline recovery must take two actions. First, the pipeline recovery logic creates a bubble signal to nullify the computation in the following stage. And second, the recovery logic triggers a flush train signal, indicating the ID of the stage that generated the error signal. This flush train signal propagates in the opposite direction. At each stage that the flush train visits, a bubble replaces the pipeline stage. When the flush ID reaches the start of the pipeline, the flush control logic restarts the pipeline at the instruction following the failing instruction. In part A, show the pipeline organization, and in the part B, it shows the pipeline timing for an error occurring in the execute stage.
Now we are going to present the conclusions. Razor allows digital systems to run correctly and robustly with minimum power consumption. Razor lets circuits to tolerate low circuit timing errors. In the example of the multiplier, the voltage can be reduced 330 millivolts below the full margin from 1.69 volts to 1.36 volts, and the multiplier will complete 98.7% of all operations without error, and it saves 35% of the energy.
Error rates are due to circuit inputs and calculation latency. As voltage continues to drop, more circuit paths cannot complete until error rate reaches 100%. As a drawback, when the processor circuitry is too complex, the elements from the Razor logic can introduce some delays and power overhead that can reduce the power savings effect. Thank you for watching.